Year 13, Chapter 19, Force and Motion, Lesson 1, Reviewing Year 1 Content. So let's have a look at this problem. We're going to draw a force diagram to illustrate the information in the question. A car of mass 800 kilograms is travelling with an acceleration of 1.2 metres per second squared. So here's our car, which is going to be modelled as a particle. It's got mass 800 kilograms, so it has a weight of 800 g newtons. There will be a normal reaction force acting vertically upwards on the car like that. And the engine has a driving force, pulling it forward, of 2,400 newtons, which means that there must be a resistance force in this direction, opposing the direction of the motion, like that. Now, we can use Newton's second law, F equals ma. We'll take going to the right as positive. It's accelerating in that direction. So the resultant force is 2,400 minus the friction, which is equal to 800 multiplied by the acceleration of 1.2. We can then rearrange this to calculate the value of F. This gives us F equals 1,440 newtons. So it's important that we refresh our memories on the vocabulary of modelling, which you will have learnt about last year in Year 12. Modelling cuts to the heart of mechanics. We take a much more complex problem in the real world and we model it using a simplified set of scenarios. So let's start with the concept of a particle. This is where we model an object as a single point with negligible dimensions and all of the mass is concentrated at that single point. So we might model a car as a particle. All models have their limitations, but they give us a good approximation. And what you can do is test your model, see if it gives you good results, and if not, you might need to go back and refine your model. So a rod. Now, a rod has one dimension small in comparison to another, so it might have a specific length, but it would then have a comparatively small width. So we would consider a rod to be one-dimensional, and they're usually considered to be rigid as well, which is a word we will come to a little bit later on. So we might model a plank of wood as a rod. Imagine a seesaw. We would model a seesaw as a rod. When you study the moments topic, you will do a lot of work on seesaws. Now, we quite often say that particles are light. A light object has a mass that is considered to be negligible, i.e. its mass is considered to be so small compared to other objects that we do not need to include it in calculations. We take it as 0. So, for example, we might say a particle is attached to a light string. A string passes over a light pulley. That means when we're calculating force and motion calculations in a particular problem, if we have modelled something as being light, we don't need to take the mass of that item into account. Let's look at some more words that you have come across previously. Smooth. If a surface is smooth, there is no friction between the surfaces and objects in contact. So we can ignore friction or take friction as being negligible. So we take the frictional value to be 0. The size of the frictional force can be considered to be 0 if a surface is smooth. So we sometimes have a particle on a smooth surface. We sometimes have a string passing over a smooth pulley. The opposite of this is, of course, rough. If a surface is rough, that means a frictional force exists between the surfaces and objects in contact, which means we must include friction in our calculations. For example, a particle is at rest on a rough surface. That means we have to look at the frictional force. Now, if an object is uniform, its mass is distributed evenly across the body of the object, so its length, area and volume. For example, a uniform rod is balanced on a pivot, and you will look at this when you look at the moments topic. So this is a situation where we might have a rod balanced on a pivot, and if the rod is uniform, that means its centre of mass is directly at the centre of the rod acting downwards, which means its weight acts at the centre, the geographical centre of the rod. The opposite of an object that is uniform is an object that is non-uniform. Inextensible, inelastic. Strings that are inextensible or inelastic do not stretch. Now, the important point then becomes that tension is constant throughout the string. So a typical example, particles are attached to either end of an inextensible string. So, for example, in a pulley system, now if we know that the tension is constant throughout the string, we know that acceleration is going to be constant when the system is set in motion. And this can then allow us to use our equations of constant acceleration, our Suvat equations. If an object is defined as being thin, that means it has a definite length but negligible thickness or width. So, for example, a particle is attached to a thin wire. And an object that is rigid, quite often rods are described as rigid, are objects that cannot bend or buckle. So a tow bar joining a car to a trailer is modelled as a rigid rod. Now that's quite important because you could tie a trailer to a car in different ways. You could use a rigid rod like that, which is fixed, or we could tie them together with a rope, which of course would not be a rigid item. It is really important that we understand all of these modelling terms so that when they appear in questions, we know how to deal with these. Now let's remind ourselves of different types of forces. So, if an object has mass, gravity will have an effect on the mass of that object, giving that object what we call a weight. Let's imagine a particle which is on a surface. Let's imagine that the particle has a mass equal to 5 kilograms. We know that its weight will be equal to 5g newtons, where g is your acceleration due to gravity, which we take as 9.8 meters per second squared. Gravity or weight will always act vertically downwards, and you should ensure that it is clearly marked on any diagram that you use. Now, tension can appear when we have, for instance, a string. Let's imagine we have a pulley and we have a string that passes over that pulley with two particles attached to either end of that string. Now, each particle has a weight acting downwards in red, you can see those, and each particle has a tension force which is acting like that, because of course the weight of the particles will stretch the string. You can also have two particles which are attached to each other by a string like that, and the second particle will pull the first particle back with a tension force. The first particle will pull the second particle forward with a tension force like that once the system is in motion. So imagine the system accelerating like that. You can have particles which are attached by a rigid rod as well, rather than a string, and again there will be tension forces acting like that in the system. Now, thrust or compression could be described as the opposite of tension here, where something is being squashed. So let's look at two possible case scenarios. Let's imagine we're looking at the forces in a rigid rod which has particles attached to either side. Let's look at the forces on the rod rather than the forces acting on the particle. So if the forces are acting inwards like that, that means the rod is being compressed or squashed. So we would describe it as being in thrust or in compression. If the forces are acting to pull the rod outwards like that, we would describe the rod as being in tension, because of course it's being stretched rather than squashed. A normal reaction force, also known as a normal contact force, is generated when an object is in contact with a surface. The normal reaction force is always vertical. So let's take a scenario where we have a particle at rest on a surface here. It will have a weight which acts downwards, and the particle will push onto the ground because of its weight, which means the ground will push back upwards, and then you have the normal reaction force. It must be perpendicular to the surfaces at contact. So, for instance, later on you will look at what happens when we have a particle on a slope, for instance, like this. So here's the particle. Its weight will always act vertically downwards, like that, but the normal reaction will act perpendicular to the surface of contact, so the normal reaction will act in this direction there, so that it's perpendicular to this sloped surface. Now, friction is a force that opposes motion or opposes the intended direction of motion. So we did an example earlier on where we had a car which was moving or accelerating in a particular direction, and there was some kind of forwards force in its engine. Because the car is moving to the right, friction will oppose this motion and it will move in the opposite direction. Now, an object doesn't have to be moving for it to experience a frictional force. Let's imagine a scenario where an object is at rest on a surface, but we push it with a force like that to try and get it to move. Friction will oppose the intended direction of motion. Now, the particle is trying to move to the right, so the friction will act in the opposite direction, and we have to produce a pushing force that is large enough to overcome the magnitude of the frictional force to get the particle in motion. Now, a driving force, we've talked about this already. This is very simple. This is where you have an object with some kind of engine. So, for example, a car. There will be a driving force produced by the engine which takes it forwards.